Today I will talk about survival analysis, and this is one of my favorite topics, and I hope by the end of the lecture you will see why. Just to provide a quick overview, I will provide a few examples of survival analysis. Then I will talk about the setup and the features of survival analysis. Then we will talk about a few extensions of the basic survival analysis, basically a little bit more complications. Then I will introduce the survival, hazard, and cumulative hazard functions. Then we will talk about nonparametric analysis and the Kaplan-Meier survival function. Then we will talk about the parametric models, including exponential, Weibull, Gompertz, and log logistic models. And finally, we will talk about semi-parametric models, and particularly about the Cox proportional hazard model. So survival analysis is also called duration analysis, transition analysis, failure time analysis, and time to event analysis. It's been used for a long time and in fields other than economics. So there are a lot of examples from those other fields, and some of the terminology we still use today in our fields. So let me provide a few examples. One of them comes from finance, if we want to study loan performance. So borrowers obtain loans and then they either default on them or continue to repay them. From economics, we can study firms' performance over time, and we can see which ones survive and which ones exit and how long it takes them until they exit. Another example would be time to retirement or time to finding a job. If you're unemployed, how long does it take you to find a job, and what's the chance that you're going to be finding a job at any time of you being unemployed? Another example is adoption of new technology, where firms, after learning about new technology, can either adopt it or still haven't adopted it and are kind of thinking about it. So here is the basic setup for survival analysis. We have subjects, and these subjects are either people, loans, firms, or something like that. And they're tracked over time until the event happens, and that event is typically called failure. That's terminology we inherit from other fields. So if the event happens, we are saying that they're failed. And again, sometimes this failure may be a good event, such as finding a job or adopting a technology or something like that. But the word event and failure sometimes are used interchangeably. So we follow them until that time, until this event happens, or until we lose them from the sample. And you're going to say, well, how can we lose them from the sample? Well, maybe a firm has filled in their questionnaires for a number of years, and then one year they did not fill their questionnaire. So we don't know that they went bankrupt. We just know that we tracked them until that time, and at that time we don't know what happened anymore to them. Another example is if we have people who are unemployed, we track them over time, and at one point in time a person moved to another state. So we lost them from the sample, and we don't know if they found a job or not. We just know that we lost them from the sample. These we would call censored observations. And some people say, well, why don't we just throw them away? And the reason for that is because they provide valuable information until they're in the sample. So for example, if somebody was tracked for, say, 7 periods before we lost them, we know for sure that this event hasn't happened for them during the first 7 periods, and that's useful information. So the next thing to talk about is a concept called survival, and this is how long people stay in the sample. And we will also plot these functions over time, and we can see survival is 100% in the beginning. We have everyone in the sample, And then as events or as failures happen to them, that survival rate would be going down over time, and we want to see how that looks like over time. And the final term that we will talk about is hazard rates. And hazard rates represent the risk of failure, or what is the chance that the event will happen for them given that they're at this time period. So maybe that would differ over time, because in the beginning you may have certain chance of finding a job or going bankrupt or something like that, but as time goes on this may change for you. So these are the basic features that we will use. So now the dependent variable would be a duration, would be time to event or time to being censored. So it would be the number of periods, and this is what we will have recorded in the data. But the dependent variable is two things combined into one. The first one is the time variable, the length of time until the event happened, or as long as they're in the study. Basically for how long we have tracked the people over time. And the next component would be the event variable or the failure variable. Same thing. That would be a 1 if the event happened, or 0 if the event hasn't happened yet. Now to make things more confusing, instead of this event variable, we could also use a censor variable. And the censor variable would be equal to 1 if the event hasn't happened yet, and 0 if the event happened. So look at this table, and I'm completely made up those numbers just to show you. Each of the lines in the table would be a subject or a person. And suppose that the first person we tracked for 15 periods, and the event or failure hasn't happened to them yet during those 15 periods. And that's why it's a censored observation. So you see how we have completely opposite of event, failure, and censored. For the second person, we tracked them for 22 periods, and the event happened for them after those 22 periods, and therefore it's not censored because the event happened for them, and so on. So when you have your data set, make sure that you have those two terminologies very clear to you. What is the event or the failure? Is it someone finding a job? Is it repaying a loan? Is it exit from business or something like that? And the censoring is when you lose them and you don't know what's happened to them. So make sure that you know which variable you have to find in your data set. One thing that I talked about already is the hazard rate, and that would be the probability that the event would happen at time t, given that that individual is at risk at time t. And to be at risk, you only need to remain in the sample, and and so that event can also happen to you. And that hazard rate will change over time, because say the probability of defaulting on a loan may be low in the beginning because you're already checked, you have your job and things like that. But as time unfolds and things happen to you, like your marital status changes, or you may lose your job or something like that, that may the ability to repay the loan may change over time. So this is when we see that those hazard rates can change over time. Now on this slide I have a few extensions of the basic survival analysis, because it could be a lot more complicated than the simple case I provided so far. The first thing is multiple occurrences of events, or multiple observations per individual. Sometimes the event is not a clear-cut, once and for all kind of thing, and an individual may experience multiple events. So for example, someone may be at risk for defaulting, and they may negotiate the terms with the bank so that they have their loans restructured, and they enter back in the data as performing as agreed. Or a firm can adopt technology in some years but not in others. So this is when we're going to have multiple occurrences of events, and statistical software could usually handle those situations. Next complication is when we have more than one type of event, and in this case we can include codes for events like 1, 2, 3, and 4. For example, we could have a borrower may default, which is one type of event, or repay the loan earlier, which is a second type of event. And the bank may care about both of these cases because they have risk of either defaulting and losing their money, or prepayment, they collect the money a lot sooner than they had anticipated. Or firms may adopt different types of technologies, and in this case again we could have multiple events. Another interesting thing that could happen is we may have two groups of participants. So for example, we may subject groups to different types of educational programs, and then we can see how those educational programs have affected the adoption of technology. Next thing is we could have time varying covariates, in which say for example, when you obtain a loan, perhaps all your information is collected in the beginning when they check you and approve you for the loan, but it's possible that borrower's income may have changed over time, which causes default. And if you have those variables also collected over the time, then you can include those as well, rather than just having one variable per subject. Next thing that also frequently happens in survival analysis is that you could have discrete instead of continuous transition times. So instead of observing a person every possible second, you may collect information every month or every year, such as survey data. And those exits are measured in intervals, in discrete intervals. Like we know, have they exited in the prior year or not? And this is when we would get graphs that are kind of choppy over time, depending on what the time period is, because it's not a continuous transition time. Another thing would be that there may be different starting times. So instead of having our study starting at time 0 and everyone is tracked over time starting from that time, some subjects may be tracked from before, have different starting times. So for them, we would need to measure the time from the beginning of their time to the event and keep track of that. Again, all of these different kind of situations, it's possible to account for them in the software. Once you know the basics, then it's easy to account for those. So on this slide, I have things defined in a more mathematical way, and we will talk about survival hazard and cumulative hazard functions. The dependent variable, duration or time, is assumed to have a continuous probability distribution f of t. And the probability that the duration time will be less than t is capital F of t, and it's right here, capital F of t, and that would be the probability that this duration would be less than or equal to time t, and that would be the integral of f of s ds. So this is the probability of this duration time being less than t. The survival function would be just the opposite of this duration time until failure, and that will be the probability the duration would be at least t. So st would be 1 minus ft, or that would be the probability of t being greater or equal than small t. So again, you have the failure, what's the probability of failure, and this is what is the probability of survival being greater than that cutoff period. So the hazard rate would be the probability that the duration will end after t, given that it has lasted until t. So this is what is the chance of a failure at that time, but given that it has lasted as long, given that that person has survived at least that much. And this lambda of t is a very important parameter, and those hazard rates, we will keep talking about them in the next slides. So that's the probability that an individual will experience the event at time t, while that individual is at risk for experiencing the event. And when we say at risk, we are just meaning that they're in the sample and we're tracking them, like we haven't lost them due to either censoring, we don't know what happened to them, or due to the fact that the event happened for them. Next, I will talk about nonparametric models, and that's useful for descriptive purposes and to see the shape of the hazard and survival function before we estimate parametric models. So I have produced here a simple table with fake numbers just so that you see how things are calculated. So one thing that we will do is go over the table, and on the next slide, which I cannot show you here simultaneously, but I'm looking at it while I'm recording, and you probably should look at your notes while you're listening to me. This is the procedure of how to interpret this table. So the first thing to do is we sort the observations based on duration from the smallest to the largest, from T1 to Tn. So let's see, this Tj is the time periods in the data. So suppose that the event hasn't happened to anyone before time period number 3. And in that time period number 3 or 4 or 5 and so on, and we will have all the time periods here listed. So this is the time variable that is part of your data set. We're ordering them in an increasing order of magnitude. So the number of risk Nj is simply the number of observations that have had this duration of 3. So suppose we have 100 people in the sample that have a duration of 3. And the number of events, we know that after 3 periods, dj is that event or failure happened to 10 of them. The number of censored observations, suppose that that is 3. So these ones, we know that we lost and they're no longer in the sample for future periods. We don't know what happened to them after period 3. We just know that we lost them, but the event hasn't happened to them. And so the hazard function that we talked about, lambda, would be equal to dj divided by nj. So we would have to how many subjects the event happened or the failure happened divided by the total number of subjects that are in the pool or at risk at that time. So that would be 10 divided by 100, and that would be 0.1. So 10% of the sample at that time experienced failure. So the cumulative hazard function, well, in the first period would be just 0.1. That number is the same as this one. Next, the survival function would be 1 minus the failure function. And the failure or the hazard rate would be 0.1. So the survival would be 0.9. So if you lost 10% of your sample, 90% continue. So come this next period, which is in period number 4 in the sample, what happened? Now the number of risk are 100 that we had before from here. 10 we lost because of they experienced the event or the failure, that's the number here, and 3 we lost because of censoring. We don't know what happened to them. So in period number 4 we're starting with 87 people. So let's suppose that now for those 87 people, 3 of them had the failure event, 2 of them we lost to censoring. We don't know what happened to them. So the hazard rate would be equal to 3, those that experienced the event, divided by 87, those that are at risk. So we would have a hazard function of 0.03. So this one, look at how much it's smaller, and it could be any number here. It will vary over time. So in this period, we have 3.4% of the subjects failed. So the cumulative hazard function, we would just accumulate it, this plus that, and we would have 0.1 plus 0.034, and we would have 0.134. The survival function, on the other hand, would be 0.9. Those are coming from the previous period, and you would multiply that to the ones that are surviving from this period. And who is surviving? Well, all of them that didn't have the failure. And these are the ones that had the failure, so all of them that didn't have the failure is 1 minus them. And that would be 0.87. So you take the survival from last period, you multiply times the survival at this period, and then you get the survival, the cumulative survival so far. Okay, so let's do one more row. In the next period, period 5, we're starting with 87 observations from previous period. 3 we lost because they had the event. 2 we lost because of censoring, so we have 82 in the pool. Let's suppose 6 of them experienced the event, 1 of them was censored. What's the hazard function? 6 experienced the event divided by 82 that started in this period, so we have 0.073 for the hazard function. Then the cumulative hazard function, you're just accumulating what we had before plus for this period, and we have 0.27. And for the survival function, we would have what's the survival on all the periods up until now times the survival rate for this period, which is 1 minus that failure rate here. So we have 0.81. And so on. You go through the whole data and you have as many lines here as they are the number of periods that are included in the data. So one thing now that I want you to think about is think about the shapes of the hazard function and the survival function plotted over time. And in the next video you will have examples, but think about what those would be in this case. So we have the number of periods here, 3, 4, and 5 on the horizontal axis. On the vertical axis, if we have the hazard function, we would plot 0.1, 0.34, and 0.07. So it would be 0.1 coming down and going up. So it won't be any monotonic or anything, and this hazard function would change over time. For the survival function, on the other hand, we would have a strictly non-increasing one. You're going to say, why not decreasing? Because you may not have failures or losing anyone for that period, and in this case it would stay the same. So we would always start with 100% in the very first, in the beginning, and then we would have 0.9, 0.87, 0.81, and so on until we go to the last period. And that's how that survival function will look like. And again, see the example in the next video. Okay, so on the next slide, I have what I have talked about in the previous slide, only written up with more math notation, but it's again the same thing. We're sorting the observations, then we're determining which ones are at risk, for how many the event happened, the number of censored observations. The hazard rate we calculated as the proportion of the events divided by all the numbers at risk. The Nelson-Allen estimator of the cumulative hazard function, we're just summing up those hazard rates over time. And the Kaplan-Meier estimator of the survival function is we're taking the product of everyone who's in the sample minus those that have the events. This is the survival rate divided by all of them, and you're multiplying those over time. And so when you're writing your paper, it would be good to have this formula in your paper. And I also talked about the decreasing step function with a jump at each discrete time event. Why? Because we have 3, 4, 5, 6 periods and so on. So this is going to be discrete time period. And without censoring, the Kaplan-Meier estimator would be just the empirical distribution of the data. So when did the events happen over time? So now we will switch gears and we will talk about the parametric and semi-parametric models. And once you have looked at the shape of these hazard functions, survival function, and so on, then you can go ahead and include some additional independent variables that may affect those functions. So we will consider several parametric models, and they assume different parametric forms for the hazard function. So let's look at the simplest one, is the exponential distribution, and the hazard function lambda would be just a constant gamma. So the survival function that corresponds to this hazard function would be exponent of minus gamma t, and t is the time or the periods that we have our study at. So notice one thing is that the hazard function is constant over time, doesn't have a t in this expression, which means that if you have time on the horizontal axis, the hazard function would be just flat over time, which means the probability of you experiencing the event, given that you've lasted so far, isn't changing over time. Now, so it's a restrictive assumption, right? And the survival function, it's an exponent of a negative number, so we would have a decreasing, slowly decreasing function, and so on. Now, these also change with time, so they're a little bit more complicated, and the survival functions are getting much more complicated over time. And I would say for your paper, estimate all of them, but as you can see from the example that I will provide later on, all of these models are providing almost identical results in practice. So just maybe pick one of them, and you can use that for your paper. The last model that I will talk about here is the Cox proportional hazard model, and the hazard rate in the Cox proportional hazard model is defined as follows. Lambda of t given x and beta is lambda 0 of t times exponent of x prime beta. So here we have the base hazard function that only changes with time, and then the the x's come in via multiplicative way to the hazard function. So that's how we put those x's into the hazard function. So I have here a note on the estimation of the parametric models. So when we estimate these models, we typically report both the coefficients and the hazard ratios. And the way to interpret things, and this is a little bit confusing, so I had to spell it out, we would have that a positive coefficient means that the independent variable increases, the time to event decreases. So if we have, again, if we have the independent variable increase, then the time to event decreases. This means that we have a lower duration, or more likely for the event to happen. Why? Because we have only, if we have fewer time periods, this means lower duration, and this means that it's more likely for that event to happen in order to have this lower duration. An interpretation of hazard rates is that a hazard ratio of 2 would mean that a 1 unit increase in the x variable, the hazard rate would increase by 100%. Or if you have the case of the hazard ratio being 0.5, then the hazard rate would be decreasing by 50%. So a hazard rate greater than 1, meaning that the event is more likely to happen, and less than 1, meaning less likely. So here's the correspondence between coefficients and hazard rates. If the coefficient is positive, that would lead to a hazard rate greater than 1. This would mean lower duration or higher hazard rate, so more likely for the event to happen. And negative coefficients would have hazard rate between 0 and 1. This would mean higher duration and lower hazard rates, or less likely for the event to happen. Now, this is also, there are two sources of confusion when you do survival analysis that you really need to pay attention to. The first one I talked in the beginning of this video, and you have to make sure that you know which one is your event/failure and which ones are censored, because sometimes textbooks or papers are using those interchangeably. So the event or the failure is what we're looking at, and the censored is when we lose them from the sample and we don't know if the event happened to them. The second source of confusion here is that some software, as I will show you later, give opposite signs of other software. So it's possible that you may estimate your model and then you interpret everything in the opposite way of the way you should be interpreting. So please make sure you watch the next video and you pay attention to that. Again, positive coefficients would lead to hazard rates greater than 1. We have lower duration, higher hazard rates. And negative coefficients, meaning hazard rate between 0 and 1, higher durations and lower hazard rates. So thanks for watching this video, and please join me for the next video when I will talk about the example for survival analysis.